Recent reports claim Reuters tested a Tesla Robotaxi in Dallas, suggesting the technology is ready for unsupervised deployment. But the reality is far more complex than the headlines suggest. The gap between this limited footage and the engineering requirements for true autonomy is where the real story lies. By the end of this analysis, you will understand exactly why the current systems are level 2+ with high confidence, not the level 4 or 5 vehicles that the narrative implies. Let us start by looking at what those reports actually show. The footage captures a narrow, happy path of sensor fusion in controlled conditions. It is a specific moment where everything aligns perfectly. The camera sees a clear lane. The radar detects a stable speed. The software predicts a smooth trajectory. This is the ideal scenario that every autonomous system is designed to handle. However, this does not prove the system can handle the long-tail edge cases that define real-world driving. Here is the thing that the marketing narrative often obscures. A system that works in perfect weather on a straight road is not the same as a system that works when the road is covered in snow or when a pedestrian is partially occluded by a parked truck. The current architecture relies on a statistical probability of safety rather than a deterministic verification of all possible failure modes. This means the system is betting on the likelihood of a safe outcome, not guaranteeing it through formal verification. Consider the specific hardware constraints of the Tesla vision-only stack. Traditional autonomous vehicles often use a mix of LiDAR, radar, and cameras to create a redundant 3D semantic map of the environment. If one sensor fails or provides conflicting data, another sensor can cross-validate the information. Tesla has made a different engineering choice. They prioritize latency and compute efficiency over explicit 3D semantic mapping. This creates a fundamental gap between the ready narrative and the engineering reality. Without multi-sensor cross-validation, the system must rely entirely on its visual interpretation to resolve conflicts. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This trade-off becomes critical when you look at how the system handles unpredictable human behavior. In a complex construction zone, a worker might wave a hand to direct traffic, or a child might run out from behind a barrier. A system that relies on statistical models trained on historical data may not recognize these novel patterns immediately. It might interpret the situation as a static object or a non-threat. The lack of explicit redundancy means there is no second opinion to override a confident but incorrect visual interpretation. User reports from Dallas indicate that the system still requires frequent human intervention during these specific edge scenarios. This suggests that the edge case handling capability is not yet robust enough to support the unsupervised claim without a safety driver present. The disparity between the limited scope of the Reuters test and the full operational design domain highlights a critical truth. The current FSD versions are effectively level 2+ with high confidence, not level 4 or 5. They lack the comprehensive sensor fusion and redundancy layers necessary for unsupervised operation in all weather and lighting conditions. Now consider the ethical implications of this gap. An RxIve paper on Tesla's autopilot ethics and tragedy points out that relying on statistical probability introduces a risk that cannot be fully quantified. When a system fails, it is often because it encountered a scenario that fell outside its training distribution. This is the definition of an edge case. In a dense urban environment, these edge cases are not rare anomalies. They are the norm. A construction zone, a flashing traffic light, or a confused pedestrian are common occurrences that require a level of robustness that current vision-only stacks have not yet demonstrated at scale. The argument for readiness often conflates speculative financial models with unverified operational claims. While GitHub repositories detail standard autonomous driving components like YOLO for object detection and SegNet for semantic segmentation, these are academic implementations. They do not represent the production trade-offs of a fleet running in the real world. There is no benchmark data or practitioner perspective from the Dallas trial that substantiates the claim of unsupervised autonomy. The absence of this data creates a critical knowledge gap that must be acknowledged. To understand why the system struggles, imagine a pilot flying a plane in perfect visibility. They can navigate easily. But if the fog rolls in and the instruments fail, the pilot needs a backup system to land safely. Tesla's current approach is like a pilot who has never flown in fog and relies solely on their eyes, assuming the weather will always be clear. The statistical model is the assumption that the weather will stay clear, When it does not, the system has no formal fail-safe mechanism to override its own confusion. This is the core of the engineering challenge. The system is designed to learn from data, but it cannot learn from every possible future event. It must generalize from the past. When the present deviates from the past in a way the model has not seen, the system can fail. The lack of explicit 3D mapping means the system does not have a deep understanding of the physical space. It has a probability distribution. When that distribution is violated, the system does not know how to react with the certainty required for unsupervised operation. The conclusion is stark. The narrative of a ready robotaxi is premature because it ignores the fundamental limitations of the current architecture. The system is impressive in its ability to handle the known, but it is not yet proven to handle the unknown with the safety guarantees required for public deployment. Until the engineering community can demonstrate formal verification of failure modes and robust redundancy layers, the claim of unsupervised autonomy remains an aspiration rather than a reality. The gap between the happy path and the messy reality is where the true test of autonomy lies. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.